Yep.
For the introduction. So today I will be talking about efficient stabilizer entropies for quantum computers. And this work was done in collaboration with Tobias, who just gave the talk, and and you can access the paper using the archive app as well. So here's a quick overview of the presentation. To begin with, I will motivate our work by discussing the open problems involving non-stabilizerness and its measurement. Secondly, I will introduce and walk through the algorithms that can efficiently measure stabilizer entropy. Then in the following part of a new measure of non-stabilizerness called Tallis stabilizer entropy will be proposed. And having introduced these tools, I will then finally connect to some potential applications. Okay, so you must be very familiar with this by now, but in universal quantum computation, we use a combination of Clifford and non-Clifford operations. And an important task is to quantify the degree to which a quantum state cannot be prepared by these Clifford operations. And to do so, the resource theory of non-stabilizerness, also known as magic, has been put forward, where non-stabilizerness is a necessary resource for quantum advantage, though not sufficient. We look at stabilizer entropies in particular, which is one of the known measures of non-stabilizerness. And stabilizer entropy is related to various properties of quantum states, such as phase transitions, entanglement spectrum, participation entropy. And it also is connected to quantum chaos and scrambling, and in particular has direct relations to out-of-time ordered correlators, also known as photocs. These properties make stabilizer entropy highly interesting for experimental studies of quantum computing. However, applications have been previously limited by measurement protocols that scale exponentially with the number of qubits. And as discussed in Tobias's presentation, it was recently shown that efficient algorithms exist for matrix product states on classical computers. However, measurement of stabilizer entropy on quantum computers remained difficult. Okay, to understand why we have this exponential scaling of measurement, let's look at the definition of Renyi stabilizer entropy, which a lot of you guys must be familiar with. So for n qubit state psi, the Renyi stabilizer entropy is given by this expression here, where n is the index of stabilizer entropy, that's a small n by the way, and p is the set of 4 to the power of n polystrings. And polystrings are just n qubit tensor products of the poly matrices. And the stabilizer entropy, Renyi stabilizer entropy, is a faithful measure of non-stabilizerness for pure states and are invariant under Clifford unitaries. They also have this additive property, which is nice. But the challenge in the measurement of stabilizer entropy comes from this AN, the measurement of the nth moment in the poly spectrum, and this is due to the summation over exponentially many polystrings. So the natural question to then ask was, how can we efficiently measure this AN so that we can efficiently measure stabilizer entropy? And in the light of this problem, our paper, we show how to efficiently measure stabilizer entropies with integer index n greater than 1 on quantum computers and simulators. So we provide 2 algorithms using Bell measurements over 2 copies of state, efficient protocol for other properties such as photocs and multifractal flatness, and efficiently computable bounds to other non-stabilizerness monotones. Okay, moving on to algorithm. I will firstly introduce algorithm 1, which can efficiently measure SE for odd n greater than 1. So firstly, we consider AN as the expectation value of this observable gamma using the replica trick. By that, I mean, we've expanded the powers of state as tensor powers. And we've introduced gamma, which now contains the summation over the exponentially many polys. So instead of summing over exponentially many poly operators, we can evaluate a single operator over multiple copies of the state. And that's why we've used the replica trick. It can be shown that for odd n greater than 1, this AN is unitary and Hermitian with 2 possible eigenvalues, -1 or +1. Whereas for even n greater than 1, this is now a projector with eigenvalues 0 or 2 to the power of n. So to measure this gamma, we transform the operator into a diagonal eigenbasis. And it turns out that the gamma operator can be diagonalized by the Bell transformation, U Bell. That's the Bell measurement. So each of the measurements with the above equation involves two small n copies of psi. However, as each Bell transformation of equation acts only on two copies here, it is sufficient to prepare and measure two copies on a 2 big N qubit quantum computer simultaneously. And AN can then be computed via post-processing of Bell measurement outcomes. And we do this by checking the parity of odd and even index qubits. Okay, this is pseudocode that illustrates the protocol of algorithm 1, which I just explained. You don't really have to know this, but the main takeaway from this is that we can see that the cost will be mainly determined by the L repetitions here, which is the number of measurement steps. So we bound the number of L measurement steps using Hofstadter's inequality. And so to estimate AN with this accuracy and failure probability, we require at most this number of measurement steps, where the delta omega is the range of eigenvalues of gamma. So we've previously shown that for odd n greater than 1, our eigenvalue has to be either -1 or 1. Whereas for even n greater than 1, our eigenvalue is either 0 or 2 to the power of n. And so based on this, we can quickly deduce that our eigenvalue spectrum will be equal to 2 for the odd case, and our cost will scale with 1 over epsilon to the power of 2. That comes from this inequality here. And the small n appears from the parity checks that we do during the post-processing stage. And for even case, our eigenvalue spectrum diverges and will require exponential number of L. So what this means is that algorithm 1 will be efficient for odd n greater than 1, but not efficient for even n greater than 1. So to tackle this, we introduce algorithm 2, which is efficient for any integer n greater than 1. But this algorithm will require access to the complex conjugate state psi star. But in algorithm 2, we rewrite this stabilizer entropy as a sampling problem over the probability distribution of polystrings. So this is the circuit for the algorithm. We firstly prepare the tensor product of psi and psi star on the quantum circuit and transform into Bell basis. Then we sample from the 2 big N qubit state in the computational basis, gaining outcome of either 0 or 1. And we have psi such that the computational basis state corresponds to the bit string. And so the sampling from the Bell basis state corresponds to sampling polystring sigma r. This means that the resultant measured eigenvalues have 2 possible values, +1 or -1. And so the number of repetitions L of this algorithm is such that the required number of copies of psi is independent to the number of qubits, which is exactly what we want. However, we note that our psi star cannot be efficiently prepared in general with black box access to our state psi. But with circuit description of unitary preparing the state, this complex conjugate state can be constructed by an element-wise conjugation, meaning that it will be efficient. But this is a special case, so not always. So now we introduce the measure, well, a new measure of non-stabilizerness, which we call Thales stabilizer entropy. So the expression of Thales stabilizer entropy is very, very similar to Rennie's, but slightly different as we no longer have the logarithm in the expression, but the rest is the same. And of course, our Thales entropy can be efficiently measured for integer n greater than 1 using our protocol, since that's just AN. So we have a direct relationship between Thales stabilizer entropy and Rennie stabilizer entropy, which makes Thales stabilizer entropy also a faithful measure of non-stabilizerness that is invariant under Clifford unitaries. But we lose the additivity property during this process. But we provide numerical evidence that Thales stabilizer entropy is a strong monotone for n greater than 2. And this is while the Rennie stabilizer entropy that was shown in the previous presentation is not a strong monotone for any n. So maybe this is good. Now we provide efficient bounds on 3 magic monotones, robustness of magic, stabilizer extent, and stabilizer fidelity. So these non-stabilizerness monotones tends to be numerically infeasible to compute beyond 5 qubits, but our algorithm can provide some efficient bounds for integer n greater than 1, as shown here. And we also give some lower bounds on stabilizer fidelity. And now I will show the results on the study of Thales stabilizer entropy with Bell measurements on the IonQ quantum computer. So we investigated the stabilizer entropy of random Clifford unitaries doped with NT number of non-Clifford gates, where we expect with increasing NT, the state would transition from efficiently similar-level stabilizer states to intractable quantum states. And the state prepared by the quantum computer will not be pure, but degraded by noise. So we error mitigated Tn by assuming a global depolarization error model. We did this particularly because stabilizer entropies are faithful measures of non-stabilizerness only for pure states. And this is figure A, where each value has been averaged over 6 random instances, and we show the mitigated, unmitigated, and exact stabilizer entropies, well, Thales stabilizer entropies for n equals 3. And we find that the results on the IonQ quantum computer with error mitigation align closely to the exact values. And the Thales stabilizer entropy is 0 for NT equals to 0, and then increases with NT until it converges to our black dashed line, which is the average value of Haar random states. So that's as expected, which is good. And we use the mitigated results of T3 to compute the upper and lower bounds for the stabilizer fidelity using this equation here. The measured results does give valid bounds on the exactly simulated stabilizer fidelity. It's just that although we find that the upper bound is relatively tight, the lower bound is non-trivial only for low NT states. So maybe this is something that we can work on. And in figure C, we demonstrate the hierarchy of bounds between the measures of non-stabilizerness. We note that our error mitigation scheme, it assumes a global depolarization error model, but works well for more complicated noise profiles. And we think that might be because of the self-averaging effects of stabilizer entropy, because there are moments of exponentially many polystrings. So that might be the reason why we see good performance. Moving on to applications. So the first application is on out-of-time ordered correlators. So these OTOCs describe how much the unitary U's spread the information, but they're challenging to measure directly and often require an inverse of the time evolution. And so using our proposed algorithm, we can now efficiently measure this average for endpoint OTOC. And this is expressed as such. So this quantity describes the average spread over both local and global polystrings, but basically can be interpreted as how much our U's scramble sigma in respect to sigma prime, where sigmas are our polystrings. But using choice state and the known relationship between OTOCs and the Rene stabilizer entropy in this first reference here, we can quickly deduce that this is true. And this means that for odd n, we can efficiently measure OTOC for 4 endpoint OTOCs using algorithm 1 alongside the preparation of the choice state. Whereas for even n's, we would also require the complex conjugate of the choice state. Maybe as a side note, you can also use ricochet property to quickly deduce this efficiently if you know the unitary U star or U dagger. The second application is on participation entropy, which quantifies the spread of the wave function over basis states, and multifractal flatness, which measures the flatness of this distribution. So our F can be averaged over the group of Clifford unitaries, and this has been proposed as this averaged multifractal flatness value. And our algorithm 2 allows us to efficiently measure this F bar, whereas it would have been difficult to measure directly otherwise. This was a direct result from the third paper. In summary, we showed how to efficiently measure stabilizer entropies with a cost independent of qubit number n, which is an exponential improvement over previous protocols. And for integer n greater than 1, our protocol is asymptotically optimal, where for odd n greater than 1, we would be using algorithm 1. And for even n greater than 1, we'd be using algorithm 2 in addition to the preparation of the psi star state. Our protocol is easy to implement, and we also were able to demonstrate efficient bounds on non-stabilizerness monotones, which otherwise are difficult to compute beyond the peak limits. Okay, that's all. Thank you for listening.
Okay, so any questions for Soovin?
Thanks for a nice talk. So you said that the Salis entropy, you numerically kind of studied the strong monotonicity with Salis entropy for n is greater than 2. So how many qubits did you check, and like what kind of numerical experiments did you do? Because like the code example seems like a very particular specific form. So for instance, like random sampling might not work. So like what kind of thing did you do?
So we did this by using numerical optimization, though I'm not exactly sure which qubit number we went up to. But basically, we just prepared some random state and then measured the non-stabilizerness before and after objective measurement. And then we checked the inequality relationship between the average non-stabilizerness of the two outcomes, and then we optimized until we could find violation, which we could not. But obviously we only just numerically shown it, so maybe like someone can try to prove it or refute it for a proper confirmation.
Yeah, thanks.
I have a question. So how is the robustness of this magic monotone for noise? Is it robust or not? Because after noise it become mixed state, and this magic is defined for pure state.
Yeah, right. So we can measure the Tallis stabilizer entropy for mixed states, but it's just that it just won't have much meaning to it because we will be violating.
Yeah, but from the experiments you have, unmitigated and mitigated, it looks close. The eye trap, yeah.
Yeah, this one.
And most for, when NT is large, very robust. Do you know the reason?
So we thought that after error mitigation, it would work well. And so I mentioned this briefly, maybe because of the self-averaging properties, while we're taking the expectation values of the polystrings.
Okay.
But maybe like an additional comment is that maybe it could have some relation to poly twirling, where we take random poly measurements and then we average it, and then we would have depolarization error model. And so like maybe this naturally kind of does that. And then by assuming a global depolarization error model, we are like actually mitigating it correctly.
Yeah, thank you. Okay. Any other questions? Okay, if not, let's thank the speaker again. Now, all the speakers on this very stable session.